Okay, so I'm recording. Let's go ahead and share the screen again. Okay, so let's try this over again. You guys were talking about implicit differentiation, and I had mentioned that the differentiation we've been doing for the whole semester has been called explicit. And the difference is how your functions are defined. So an explicitly defined function looks like either f of x equals, something over here. Let me actually put an example. So maybe I have f of x equals 3x squared plus 5. Or if it was just y, it would look like this. We call these two functions explicitly defined because your output variable is by itself. So I am explicitly defining this y as a function of x. So let me show you what an implicitly defined function looks like. It's still a function, but it's just the output variable is not by itself. So what if I had 3x plus 4y equals 10? So you guys, this is still a function of x. You know that y is an output variable and x is the input. So it's still a function of x, but it's not solved for y. And on this one, honestly, it's not that hard to solve for y. But in some of the cases we look at today, it would be hard to get y by itself. So instead of just getting y by itself and then taking the derivative, I'm just going to do it implicitly. So this y, we haven't really talked about y that much. I say, what's the derivative of y? And then we end up just kind of leaving this alone. We call it dy dx or just y prime, or if it's in function notation, we do f prime like this, but we don't actually talk about what's happening to this y on this side. And then we just take the derivative of everything over here. Today, we're not going to be able to do that. We're going to have y's showing up on possibly both sides of our equation, not alone. Sometimes they're going to be together in a term, x and y. So I just have to figure out how to differentiate implicitly, which means we need to talk a little bit more about y. So you've got a variable y. I know it stands for the output of the function. If I want to take the derivative of y, and I do it all the time, you guys, I write it like y prime. Or today we're going to really focus on writing it as dy over dx. So this says to me the first derivative of y, but this also says this, you guys. This is, if you were to say this, you would say the first derivative of y with respect to x. So with the respect to, it means that x is the input variable in the problem and x is the value that's changing. I want to know how this function is changing as x is changing. So a lot of meaning goes into that with respect to x. So yes, it's always there. We just really haven't had to think about it that much. So y is a function of x. Let's think about this. If I told you I wanted you to take the derivative of x squared plus 3 to the 5th. Well, I know, because we've done this quite a bit at this point, that I need some chain rule. You guys, I treat this like it's just an x for a minute, right? And I say, oh, if this was just x to the 5th, what would I do? And I bring the power rule down around it, and I leave this the same. And I get that, but remember that extra step that I have? You guys, this is not just x. This is some function of x. And because it's not just x, I have to multiply at the end of this problem by the derivative of what's in here. And so again, we're all probably pretty good at the chain rule by now. And what we're going to do with implicit differentiation today is the same thing. We are doing the chain rule. So let's look at this let me change this just a little bit. So I had x squared plus 3 to the 5th, and I know how to deal with that. But what if I had y to the 5th? Remember, our y is not going to be alone today. It might have a power on it. If I remember that y is actually just a function of x, just like x squared plus 3 is a function of x, I can differentiate this using the chain rule. So watch. Using the chain rule, what do I do with this in here? I pretend it's an x for a minute, right? And I say, okay, if that was just an x, I'd bring the 5 in front. I'd leave this the same, and I'd put it to the 4th power. But then I would add on the chain rule and say, okay, now I have to, because this is not just an x, well, it's not an x at all, right? I have to multiply by the derivative of what's in here. So I think back, oh man, but what's the derivative of y? Well, you guys, we write it like this. That's the only way we know how. If I don't know anything else about y, but I need the derivative of y, I'm just going to call it the derivative of y with respect to x. So I really need to be clear about the similarities between these two things. We haven't ever had to really take the derivative of y raised to a power, or the product of y and something else. You guys, anytime you see a y in your problem today, notice that the power rule around y worked the exact same way that it did around x, just like it did here, around this term. It's just that that wasn't just an x in both cases. This was not just an x. So we used some chain rule, and we might multiplied on the derivative of that inside term. So if your inside term is y, remember the derivative of y, we just write it this way as derivative of y with respect to x. So remembering chain rule as we work an example. Let's go ahead and do this one that I had here. We have 3x plus 4y equals 10. Now again, you could solve for y pretty easily. And if I got y by itself, I would just take the derivative explicitly, because it would just be y equals whatever function of x, and it would just be a normal derivative. But I'm not going to get y by itself. I'm going to leave it in here. You guys, just like I usually do, I'm going to take the derivative of each term, and let's see what happens, you guys. So the derivative of 3x, well, I know that that's just 3. That's just a normal 3x. I deal with x all the time. Let's talk about the derivative of 4y, though. So all the derivative rules apply on any variable. So this 4y, it is going to come down as a 4. Remember, you treat it as if it were an x. You take the derivative just like it was an x. If that was 4x, I would just be bringing down a 4, right? But then the chain rule happens, and I say, okay, but that wasn't just an x, it was a y. So I tack on the derivative of y as dy dx. And we're going to use that as a term today. And algebra works on it just like anything else. Just like we have x or y or z or whatever, this is just a term we're going to use. Now 10 is a constant, right? So on this other side, when I take the derivative of 10, I get 0. No x's or y's in there. So look what I have. And I'm like, well, that's not very, that doesn't tell me a lot. I'm trying to take the derivative. You guys, your goal when you take a derivative, whether y is by itself or not, is always to find the derivative of y, or dy dx. And it's going to tell you in your instructions on a problem like this, it's going to say find dy dx or find y prime. Remember, that's always what we're looking for. It's just a lot easier usually. So look what I have here. I've got dy dx, and my goal is to find that. I want to know what is the derivative of y with respect to x. I don't know it right here. That's why I wrote it like this. But now that I have that dy dx term in my equation, I can isolate it and solve for it. So let's subtract 3 on both sides. And I have 4 dy dx equals -3. Remember, like I said, basic algebra works on this. Act like it's just any other variable. Divide both sides by 4. And I get dy dx equals -3/4. So it just equaled a number on that one. Sometimes it'll have a variable in there, but this one was just a number. So I want to take this function, this same 3x plus 4y equals 10, and I want to do it explicitly and see if I get the same thing. So when I say explicitly, remember that's when y is by itself before I take the derivative. So let's solve for y. So let's see, we would be subtracting 3x on both sides. And I get 4y equals 10 minus 3x. Then to get y by itself, I would be dividing everything by 4. And I get y equals 10/4 minus 3/4 x. So look, now I have a function explicitly defined where y is by itself. So let's pretend this is like, chapter 11, and I say, hey, can you take the derivative of this function? Well, yeah, I could call this y prime, but you guys, instead, I'm going to be using dy dx more today because we have to use it a lot. So yeah, I take the derivative of this because y is by itself. When you take the derivative on this side, remember that's why we just write it like this. We are technically taking the derivative of y, but when it's by itself, it's easier. So this 10/4 is a constant, right? So I get a 0. What's the derivative of -3/4 x? Isn't that just -3/4? So what did I get? Well, I got the same thing I got over here, but I did it over here without having to solve for y first. So with this chain rule business and the dy dx, I know that it can be overwhelming, adding that new thing in here. But I wanted to show you between this and this that it's actually not really new. We've been doing it the whole time. We've been finding dy dx the whole time. We just never really had to think about it so much because it was always by itself already. But we are doing the same thing. What I want you to think about today as we work some problems, anytime you have a y in a term, you're going to take the derivative however you need to, just like it was an x, and then because it's not an x, because it's a y, every term that has a y in it, when you take the derivative, gets a dy dx. So you're in your head, you're thinking, hey, there's a y there. I take the derivative, somewhere there's going to be a dy dx in there because of chain rule. So let's look at another example. I've actually got tons of examples here. Let's do this one. And I know we need tons of examples on this stuff. So what if I had this? X to the 4th plus y to the 4th equals 13. Sorry. So I look at this and I'm like, okay, well, it seems pretty simple. Notice y is not by itself. And honestly, if I did need to get y by itself here, I would have to get the x term on the other side. I would have to take the 4th root of everything. Let's just do it implicitly instead. So it says to find dy dx. So I can do that, you guys. So just think, take the derivative of each term. That's always our first goal. So what's the derivative of x to the 4th? Well, that's simple. It's 4x cubed. Plus, well, what's the derivative of y to the 4th? Well, we're going to treat it like it's any other x and get 4y cubed. Notice the power rule, I did it around it. But because this is a y, I tack on that dy dx at the end of that term. What happens to the 13? Well, it becomes a 0. And then from here, I solve for dy dx. So once you take the derivative of each term separately, making sure anytime a term has a y, it does get that dy dx in there. after that, you just solve for dy dx, and that's all there is to it. So I subtract the 4x cubed from both sides. That'll leave me with 4y cubed dy dx equals negative 4x cubed. To get dy dx by itself, let's divide both sides by this 4y cubed. And I get dy dx equals, and then just, you can reduce this fraction a little bit. We have negative 4 over 4, so we can just call that negative 1, or just call it negative. You don't even have to write the 1 in there. And then we have the x cubed over y cubed. So you could just write this as negative x cubed over y cubed. So the thing about your answers today, like on this one, got a constant powers in this problem. Notice we have x and y sitting here in our, and it's not always pretty. These don't, you know, being a nice number or something pretty with just y. Negative x cubed over y cubed is dy dx, and you don't have to go any further than that. I just got a message saying my internet connection is unstable. So you guys, if it starts popping out or something, let me know. Zoom must be having some tough times today. All right, let me get another example up. Ooh. Yes, I love this one. So I have this example. I have x squared times y to the 5th equals 16. Okay, so I'm not going to get y by itself, but I am going to take the derivative of each term. You guys, this is one term. This is a product, right? I can't actually multiply x squared times y to the 5th because they're different variables, right? What do I do to take the derivative of a product? Well, I have to use the product rule. You guys, the product, all your rules still work, even if you're using them on something with a y in it. So let's take it to the side. You guys, your u here, let's say u is x squared and v is y to the 5th. So your du, you guys, the derivative of x squared is just 2x. Your dv, though, we have to be careful. You guys, y to the 5th, it is going to be 5y to the 4th. But because it was a y, you tack on that dy dx. Now we can put it together here. So let's see, it will be u times derivative of v plus v times the derivative of u. And you guys over here, that 16 is still a constant, so it just equals 0. It's always nice when that happens. It makes our problems easier. So I want you to notice something, and it's something that it comes up, and I don't want it to confuse you because it can be confusing. Sorry. Notice this term has a y in it, but it doesn't have a dy dx. Remember that that's okay because that term came from an original term, v original, which was not the derivative. And the derivative was actually just u, and because u only had x's, I didn't need any dy dx when I took the derivative. So this y, a lot of times as people do their work and they look over this one, they're like, oh, I had that y term, I got to add a dy dx in there. Well, no, because we didn't actually use the derivative here. That was an original. It's only when we take the derivative of a y term. So let's see what we have here. What is, you know, what's going on? Now, this is all multiplication here. So you can, what you can do is we really just have two terms, right? We have this x squared term, and then we have this y to the 5th times 2x term. Remember, your only goal is to isolate dy dx. So I'm going to subtract this whole term from both sides. And then I'll have x squared times 5y to the 4th dy dx equals y to the 5th times 2x. Sorry, it would be negative, right? Because we're subtracting. Now, even though it looks really complicated, there's only one more step. You guys, you're just trying to isolate dy dx, so just divide by everything else. Now, is your answer going to look like a crazy combination of variables? Yeah, and that's okay. So we get dy dx equals negative. Usually I'll put the x terms in front. It really doesn't matter, just for, you know, it looking better, I guess. Usually any kind of coefficient like that 2 or the 5 will go in front. And then I always start with x terms and then y terms. So on top, I'm going to write that as negative 2x y to the 5th. On the bottom, I'm going to write 5x squared y to the 4th. So technically, this is your answer. There is some canceling you can do here, though. Notice on top, I have y to the 5th, and then I have y to the 4th on the bottom. So you could take a y to the 4th out of both of those, which would just leave a y on the top. What about the x's? You have x squared on the bottom and x to the 1st on the top. So if you take out an x from both of those, it just leaves an x on the bottom. And then on top, you have that negative 2, and on the bottom, you have that 5. So always reduce, because it might make it look a little better.
Do you care for us to always reduce?
So yeah, so you'll have to, and especially MATLAB will care. So you,
Okay, thank you.
yeah, getting that good habit. Sometimes you can't reduce. I mean, you know, so always try. And if you can't, that's okay. Let's see. So you guys, implicit differentiation, notice we've done a lot of power rule here, and we did a product rule. It's not restricted to that though, you guys. We could do this on exponential terms or natural log terms. I want to look at let's start with an exponential. So I want to do this one. I want to do 5x squared equals 1 minus e to the y. So I have an e term in there that I have to deal with. So you guys, trying to get y by itself here would be awful. You've got y up in a power. So you guys, when I look at this, I'm like, hey, if I need the derivative here, I'm definitely going implicitly. So let's do it, you guys. Notice there's no product rule happening on any of these terms. So these are just, you can take the derivative of each one separately. So what's the derivative of 5x squared? Well, that's just 10x equals, you guys, this 1 turns into a 0. Let's talk about the e to the y. If it was just an x, guys, you have e to the x, the derivative is e to the x, right? So you guys, if I treat this just like it's an x, I would just be bringing down e to the y. But how does chain rule work on an exponential? Remember, I bring the term down exactly the same, and then I find the derivative of that power, and I multiply it on the end, which in our case, the derivative of y is dy dx. So again, all you're doing is sticking a dy dx onto that term because there was a y. So now I'm here. Let's get rid of that 0 minus. Let's just call this negative e to the y dy dx. Remember, our goal is always to isolate dy dx. So honestly, it's pretty easy here. Just divide both sides by negative e to the y. And you would just get 10x over negative e to the y equals your dy dx. So definitely not pretty, but that's the answer. So notice the exponentials, I know they're not our favorite thing. They're one of the newer things that we're doing. So you're like, okay, now you're throwing in y's in there. Just remember, if it has a y in it, you treat it like nothing's different until the end where you stick on a dy dx. Let's do a natural log. Let's see. Let me find a good one. Okay, I want to do this one. I want to do 3 times the natural log of x equals 4 minus the natural log of y. So a couple different natural logs in here, one of x, one of y. So let's remember how natural log works. If you have the natural log of something, your derivative is always just 1 over that thing. So this 3 is a coefficient, so I know it's going to come down with me. You guys, the natural log of x, the derivative ends up being just 1 over x. Now, derivative of 4 is another 0. You get a lot of zeros here because there's a lot of constants running around. Let's talk about the natural log of y. So let's take it to the side, and that's an h. Let's take it to the side and think about it. So remember, if this was just an x and I was taking the derivative, it would just be 1 over x. But it's the natural log of y, so it's going to be 1 over y. What do you think I'm going to stick on? Because it's a y, I have to multiply by the derivative of that. So you can see I get my dy dx. And honestly, guys, on these problems, remember in the instructions it says find dy dx. So if you're working a problem and let's say you forget to add on a dy dx and you're just here and you're like, this seems right. Well, how can you find dy dx if there's not one in your problem, right? You can't solve for something that's not there. So hopefully that's a clue to help you remember, oh yeah, I need a dy dx on that y term. Because if I don't have it, I definitely can't solve for it. So you guys, this 3 times 1 over x, let's call that 3 over x. Let's get rid of the 0 minus. So let's call this minus 1 over y dy dx. Remember, your goal is to solve for dy dx. So let's divide both sides by negative 1 over y. So how do you divide by a fraction? You just multiply by the reciprocal. So over here, you're going to have 3 over x multiplied by, let's call it negative y over 1. And that's going to equal dy dx. And then just straight across the top, straight across the bottom here, get negative 3y over x as your answer. So not too bad, you guys. You'll notice that while you are going to use all the derivative rules in these problems, it's not like the hardest versions of them that you've ever seen, because this is a new method. So it's more of, I want to test you over the method. I want you to practice the method and know how to use it. This isn't the time for me to give you a bunch of crazy quotients and, you know, crazy stuff that would be hard to take the derivative of. Let me see what else I got. You guys, this is going to end up being a 2-part lesson. So next time we'll finish it. I could probably finish it today, but 1, we have tons of time. And 2, I just really feel like I want to separate it because this stuff is really important to understand, but it's also a little bit harder to understand. And knowing this stuff is going to really, really help us in the next section. So I want to be solid. I want to do a product rule with either an exponential or a natural log, or maybe both. You guys, I want to do x cubed times e to the y equals 13. I don't know why I keep writing an example like you don't know these are examples. Okay. So we're here. You guys notice product rule happening here. This is a product of 2 different functions, right? So, and you guys, sometimes knowing when to use product rule is important. And I know, you know, when we did product rule, you had to figure that out. Okay, when do I use product rule? When do I not have to? But you might have to revisit, you guys, why is this product rule? you know, why did I choose that? Well, because it's a product of two things you can't actually multiply together. Okay. So if u is x cubed, du is 3x squared. If v is e to the y, then dv, or the derivative of v, will be, remember it comes down just as is, and then you tack on that dy dx. So let's put it all together and get x cubed times e to the y dy dx plus e to the y times 3x squared equals, luckily, 0 over here. And then remember, you're just trying to isolate dy dx here. So let's see what we get. Let's subtract this term here just to get it all on the other side. So I'm going to have x cubed e to the y dy dx. Let me bring this up a little bit. Equals negative e to the y times 3x squared. Then let's divide by x cubed e to the y to isolate our dy dx. So I'll get my dy dx over here by itself. And that's going to equal, I'm going to call this negative 3x squared e to the y over x cubed e to the y. Notice there's some things I can cancel, like the e to the y's are actually just gone here. And on the x's, you can leave an x down here, and then that x squared would be gone, right? So we end up with just, negative 3 over x. So you guys, with all the product rule and stuff, this one turned out surprisingly simple. Sorry. Okay, let's see. So far, these have all been really easy to solve for. Once you take the derivative of everything and you have a dy dx in there, you try to isolate. They've been pretty easy to isolate. And honestly, for the most part, they are in your problems. I'm trying to see if there's one that might be a little tougher, but really, I'm just not seeing it here. So it shouldn't give you too much trouble on the solving for dy dx. Let's do one more. Let's do 8y times the natural log of x equals 15. So 8y natural log x equals 15. So again, can we see why we have to use the product rule here? Product of two terms that we can't actually multiply together. So let's find u and v. So let's say that u is 8y and v is natural log x. So the derivative of u, so if this was just 8x, well, the derivative would just be 8. But it's not an x, it's a y. So I need to add dy dx. Derivative of v, so you guys, this is just plain old natural log x. The derivative of v is just going to be 1 over x. So let's put it together. We're going to get 8y times 1 over x plus natural log x times 8 dy dx equals, again with a 0, you guys. So let's see. Let's call this 8y over x. We can just put those together. And I'm going to leave this the way it is. Or actually, I'm going to put the 8 in front. That'll be better. Let's call this 8 natural log x times dy dx equals 0. So you guys, get rid of the term that doesn't have dy dx in it. Let's subtract that on both sides. So we'll have 8 natural log x dy dx. On this side, 0 minus this term here. So we'll have minus 8y over x. All we have to do now is divide both sides by 8. Really, my natural logs keep getting like melded together into this weird h term. Okay, over 8 natural log x. So let's make sure we can figure out this division. So you guys, anytime you have a fraction and you're just dividing by a just a regular number, all that's going to happen is this number is going to be stuck on the denominator. It's going to join the denominator. If you need verification, take it to the side, you guys. So I have negative 8y over x. I need to divide by 8 natural log x, which is the same as multiplying by 1 over 8 natural log x. What happens? You guys, this denominator just gets bigger. So you guys, what we're looking at here is negative 8y over x times 8 natural log x. So you guys, the only thing I can cancel here is the 8's. So instead of negative 8 over 8, I'll have negative 1y on top. And on the bottom, I'll just have x times the natural log of x. Make sure you don't try to put these x's together somehow. That one x here is stuck in its natural log statement. Okay. So hopefully you guys, this isn't too overwhelming because it is so different. And remember, we are going to continue this same very thing next time. Now we're going to take it further, of course, but we are going to continue with the implicit. I'll be putting up some homework for this part 1. So questions just like this that you can work on. I'll be putting that up. I don't think I'll get it up before my next class starts at 11, but maybe after that one. But anyway, look for that. Practice this part 1, and then we'll work on part 2 next time.